Okay, this is the second video. The first one was about arithmetic sequences. Now we're going to do another video and how to generalize and write the formula for it. So I'm going to go back to the Desmos activity. This is the one that was in the other video that we just did. I'm going to go back and show you this image here. So this is something called the Sierpinski triangle, which is so cool. Okay. If any of you are like observant and cool, you have noticed that I have earrings that look exactly like this. Okay. So this has to do with, if you notice, yeah, you start with one triangle and then the triangle like gets split into three other triangles, and we're just counting the black triangles, so you can think that the white ones are kind of like cut out and not there anymore. From stage 2 to stage 3, it also, like, each individual, the smaller ones are cut and it gets smaller and smaller and smaller. This is something that we would call a fractal. A fractal is something that has an iterative pattern that just keeps going and going and going, and you do the same thing to the thing before it to get to the next one. Okay. And fractals can just get tiny and tiny and tiny. It's just like snowflakes are fractals, and like leaves on trees and things like that. Oh, it's so cool. Okay. Now, I do not want to draw this out into the notes, even though you, I think, are supposed to draw. Nope, thank goodness. I was nice to you and I told you not to draw the next one. But you could try if you want to draw the fifth stage. So I'm going to try to screenshot this and let's see if this works. Okay, fancy. I just learned how to do this on my new thingy. This is so cool. Okay, so I'm just going to take this image and I'm going to go to my notes, and you have your notes as well, and I'm going to boom. Okay, so we're calling this generalizing sequences. This is writing formulas. Yeah. So let's talk about how this is changing. We said that, I said that each black triangle is being split into three smaller triangles as you progress through the stages. So we can say from stage 1 to stage 2, well, first of all, go away. How many triangles are there in stage 1? Well, there's just one. How many triangles are in stage 2? 1, 2, 3. There are 3. You need to count the number in stage 3. 1, 2, 3, 4, 5, 6, 7, 8, 9. Do we see a pattern? Can we figure it out? I don't want to count these. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. There are 27 triangles. Do you guys notice anything about these numbers? Do you notice patterns? Do you notice how they're growing? How do you get from 1 to 3 and from 3 to 9 and from 9 to 27? Well, from 1 to 3, yeah, you can add 2. That's true. From 3 to 9, you could add 6. That's true. The only thing is, like, those aren't the same numbers, so that's not arithmetic. So maybe we're not necessarily adding the same thing. We're actually multiplying by 3. Multiplying by 3. From 9 to 27, we multiply by 3. Go ahead and start making a table for this one, just like we did in the other one. We're going to want, can I make it a little bit smaller? Yeah. We are going to, what's this? Is that another pen? Okay. We are making a table and we are counting stage number, just like before. You could also call it figure number or like diagram number or just, I don't know, term number, stage number. And over here, we are counting the number of black triangles. This would be really interesting if we talked about counting the number of white triangles, and we could see how it's like related to the number of black triangles. But if we were to count just the number of triangles total, well, that'd be interesting too. But the thing is, they would all be different sizes, and we'd have to like kind of have different unknowns for that. Okay, anyway, stage 1, stage 2, stage 3. We're going to go to stage 4 because it's there, and ultimately we are going to get to stage n. That's how we generalize with variables. So in stage 1, how many triangles were there? There was 1. In stage 2, there were 3. In stage 3, there were 9. Stage 4, 27. Okay, I just wrote this differently. I just wrote like the total of the black triangles, but that is harder to see necessarily like how it's growing. So I'm gonna compare everything to the first stage. So 3, I started at 1, and what did I do? I multiplied by 3. For 9, really, I started at 1 and I multiplied by 3 to get to the second stage. And then from the second to the third, I multiplied by 3 again. For the fourth stage, I started at 1 big black triangle. I multiplied by 3 to get to the second. Then I multiplied by 3 to get to the third. And then I multiplied by 3 to get to the fourth figure. Okay, now the question is, how many times will I be adding? How many times will I be multiplying by 3 in the nth figure? So we're going to start with 1 big black triangle because that's what it is in the first stage. And we multiply by 3, but how many times? Yeah, this was, this is 1 times 3 just one time. And this is 1 times 3 2 times. And this is 1 times 3 3 times. Can we say something about this first stage? This is 1 times 3. How many times there? Can you follow the pattern? This actually has an exponent of 0, which is really cool. Anything raised to the 0 power is 1, except for 0 to the 0, which we don't talk about. Okay. So how many times, how do we relate it to n? Remember, this is n, this is t sub n equals 1, n equals 2, n equals 3, n equals 4, and obviously n equals n. So this 0 is, compared to 1, well, this is 1 minus 1, n minus 1. This 1, compared to this 2, is 2 minus 1. This 2, compared to this 3, is 3 minus 1, okay? And this is 4 minus 1. So what is happening, we're multiplying by 3, n minus 1 times, okay? Please make sure that this whole thing is in your exponent. You could use parentheses just like I did right there. Otherwise, just make sure both of the things are like small up as an exponent. So we just need to like actually write this instead of expressions as like a real big formula for t sub n. T sub n equals, well, we start with our first term, which is 1 big black triangle. We multiply by our ratio, which is 3, and we do it how many times? N minus 1 times. And there you go. Like, that is our formula for this situation of the Sierpinski triangle. And we need to say, well, what kind of sequence was this? We said that we are multiplying by the same thing. That's something we call a common ratio. Okay, you could also call it a common multiplier. Ratio and multiplier, same thing. And we use the letter R, so we're going to use the word ratio. The common ratio is times 3, which means this is something called a geometric sequence. Yeah. If you want to talk about the type, like what the graph would look like and what kind of function, it's actually something called an exponential function. Exponential, which we have not discussed, but we will because we're getting there. And that's how we start with sequences and we talk about their functions. Yeah. So to go even more backwards and generalize this general formula, remember we want T sub n, and we take any term that we know. So it doesn't always have to be the first term. It could be, I could have started with the second term and say, how do I get to the nth term? And I multiply by my common ratio. How many times? N minus k times. I'm using k because that's the k of that term that I know. Yeah, remember this is a term that we know. If I want to use the first term, that's T sub n equals T sub 1, first term, times my ratio raised to the n minus first power. And that's what we used in the red one, okay? This is probably going to be the most common one that you use. Like you more frequently use the first term, okay? But we could also use the 0th term, which is going to be T sub n equals T sub 0. Remember, T sub 0, we're actually going to be using that when we deal with the functions. That's going to be like not what happens when n is 1, but it's actually when n is 0 or when x is 0. We think, what point happens when x is 0? That's the y value. That's going to be the y-intercept. So functions often deal with y-intercepts in 0th terms, whereas sequences will often deal with the first term. But we're always going to be multiplying by a common ratio. How many times? N minus, the letters always have to match numbers. So n minus 0. Well, n minus 0, I mean, that's just, isn't that just n? You multiply by r n times. Okay. Like I said, this one with the first term, you need to be comfortable with. Also the one with the 0th term that you should be comfortable with. Yeah? So let's do an example right now. Let's say I want us to figure out how many triangles of the Sierpinski triangle. Remember, we're dealing with this figure. How many triangles would be in the 16th? Oh, 16th. Sure. How many triangles would be in the 16th stage? Okay. This is an example. So I want to know, okay, my handwriting is really bad. I want to know how many triangles would be, okay, also how many, we're talking about black triangles. I'm sorry, I need to qualify that. How many black triangles would be in the, what did I say? 16th stage, 16th figure. Okay, to answer a question like this, you do not draw it out. Yeah, you do not just give up and say, I don't know. No, we just made an equation. Like we use the equation to help us answer these things. So let's remind ourselves what our equation is. It's this thing in red right there. So we have T sub n equals 1 times 3 to the n minus first power. You notice I did not write parentheses around the 3, and that's okay, because I just know that the exponent has to do with the 3, and it does not have to do with the 1, even though it wouldn't change anything because it's just 1. So let's figure this out. We want to know T sub 16 equals 1 times 3 times 16 minus 1. I'm sorry, 3 raised to the 16 minus 1 power. Let's simplify this a bit. 1 times 3, 16 minus 1 is 15. Okay, is that how I leave my answer? No. And I go to a calculator, And I say, what is 3 to the 15th power? So that means, oh, okay, I can't see it anymore. T sub 16 equals 1 times, let's go back to the 14, 348, 907. 14, what was it? 348, 907. 348, 907. Oh my gosh, that's so many triangles. Times 1, G, that doesn't change anything, okay? So this is just 14,348,907 triangles. Oh wait, there was a wordy question. Okay, so how do you write your answer? We would say there would be 14,348,907 black triangles. Aren't you glad I didn't make you write out and draw out the 16 figure? In the 16th stage, stage of, you can be specific, the Sierpinski triangle. That's just, what can you, that's so crazy. Yeah, here's our answer. So that is an example of how we use our formula. We wrote a formula and we used it to help us answer a question. Okay, that's why we use this formula. It helps us model problems in mathematics, all right? So this is the end of this video. I'm gonna do a couple more videos where I do examples and they're gonna go much faster. I'm gonna have some pictures and I'm gonna have some just sequences and I'm just gonna boom, 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 boom it out, okay?